Hi, Charlie. We can see your screen. You can start right now.
Okay, can you guys hear me?
Yeah.
Awesome. Sorry about that. Had a permission issue. So okay, so yeah, excellent talk by Inka, and I want to follow up with continuation on how to do planning with these kind of negotiation, and I'll talk a little bit about deep reinforcement learning, how to make it robust. So just an overview on a typical sort of autonomous systems framework. What typically you'll have is you'll have a perception stack, that module that takes cameras or LiDARs and basically does tracking or detection. And then you'll have the state of the world basically formulated for you, and then you'll do predictions, and then followed by planning, and then in the end you have the controls. So that's the typical framework, and we're gonna, for the sake of this talk, we're gonna assume that perception is gonna be really good, almost perfect. And we're gonna simply focus on predictions and planning part. So the kind of situation we're really interested in is what's known as negotiations. So imagine we're the green vehicle and we're trying to merge onto the highway. So we have to make sure that the gap is open and we can safely and robustly merge onto the highway. So this is the kind of problem. And so you might ask, well, why is this hard? Humans does this every single day. Why is this hard for a computer algorithms? And the reason is that we must be able to act in response to how other actions agents are reacting to our actions. All right, so because our actions can influence the behaviors of other agents on the road. One thing we can do is we can have really good predictions. So we had a paper last year at NeurIPS on exactly this. How do you do multimodal predictions? And this is a widely studied area. Rowan also has worked on this in the space in the past. And the idea is that if you have really good predictions, then you can then formulate this entire problem as a search problem, right? You can use predictions as the edges in this the search tree, and then find a state that in the future that you think it's going to be good. So sort of high level overview on how do we do multimodal predictions. It's very simple. You're trying to forecast the future trajectories of yourself and as well as other agents in the environment. But the key here is that you have to watch out for multiple possible future paths. So this what's called multimodal predictions, and also agent-agent interactions, right? So if you look at this example, how the different interactions of whom yields to whom really affects the future trajectory that you're able to forecast. So these are the key problems. In this work, we came up with a sort of end-to-end framework that took the state of the world at time t as the input, and then really used multiple RNNs to encode the state of each agent independently before adding context, and also then combining information, and then forecasted the sort of latent variables, discrete latent variables that can represent different modes, such as conservative driving behaviors versus aggressive, or left turn, going straight, or U-turn. These are sort of these latent discrete modes that we can then estimate the probabilities of before then using decoding RNNs to forecast the trajectory of the world, sort of unroll them into the future. So this is the architecture that we used, and this is one of many ways that you can you can learn a data-driven prediction algorithm directly from just simply pure trajectory data. So is that all we need to solve this problem? Circling back, and the question is actually, you know, I don't think it's the full solution. And the reason is because the number of possibilities will explode exponentially in terms of the number of agents you have or the interactions you have in the environment. And you really need really good predictions in order to make the system work. And then it has to be computationally feasible, right? So So we have to make decisions, typically something like every 100 milliseconds real time. So, if it takes a minute, 20 seconds to compute a really good solution, we have large number of leaf nodes, then that's not going to work. So that's all good. If you guys are interested in details, if anyone's interested in details, please check out the archive paper. But for this talk, I'm going to focus on something that's more end-to-end. So combining both the prediction and the planning module and leveraging deep RL, deep reinforcement learning for this. At a high level, deep reinforcement learning is able to let us automatically discover policies to do this instead of hand coding sort of different policy classes such as a lane change or overtake. We just want to let the deep reinforcement learning algorithm to find out the optimal policy. And so that's the advantage, but the disadvantage is that it requires simulation, and then as simulation becomes more and more realistic, the hope is that our policy would also become realistic and not overfit to the simulation. That's the biggest challenge, it would be overfitting. Okay, so for those of you who might not be familiar with RL, I'm going to give just a brief overview. So with the whole situation framework of reinforcement learning, you have an environment. This could be your simulation, or it could be the real world. And then you'll have an agent that lives in the environment, that observes certain states, and it's able to execute an action within the environment. And then the environment will provide rewards back to the agent. What we care about is one of the things we care about is the value function, which basically specifies how valuable a particular state is. And we also care about learning a policy function that really is, that tells us what sort of actions to take in any particular state. And then if we use, we can use deep neural nets for the policy function. So that's the sort of the formulation. And what we've looked at is a very simple 2D traffic simulation, 2D scenario simulation. So here you see that we have a very simple environment overlaid on a satellite image. And the goal here is that you want to go randomly from a A, B, or C location, a lane ID, to one of the D, E, or F destination lane IDs. This is known as a double lane change, or a zipper merge, and it's one of the it's a challenge because cars are trying to merge off the highway at the same time when other cars are trying to merge on. So in our case, our agents are obviously a vehicle. We're going to use a standing controller as well as a kinematics bicycle model to simulate the dynamics, and it gives us a little bit of more realism. The action space consists of both steering, acceleration, and turn signals. So here, these are some examples of what we can do to simulate different traffic scenarios. You have a roundabout, you have a left turn, and then you have different merges. So it's fairly flexible in this regard. The way we approach our representation learning is this. So we have an environment that has different agents and different velocities and different states. We need to convert that into a vectorized representation because neural nets like vectorized representation. So this is known as state encoding. And what we do is we take a top-down view and render into an image, and then we take successive images across times. In this case, the past 4 frames. And we treat it as an image, so we'll perform convolution on this. Then we also have the relative distance of the ego vehicle ourselves, the self-driving car, to the other vehicles in the environment. So these are low-dimensional relative codes. And we feed that into a policy function. So this is how we sort of encode the environment into something that the neural nets prefer and can understand. And obviously, the advantage of training and simulations that we can parallelize this. So the algorithm we use is a distributed version of PPO, and then we can create multiple environments simultaneously, and then they'll learn to update the same policy function. And these are examples of doing training. You see that it makes mistakes, and it'll restart the environment many times. Okay, so one of the interesting things we observe after training is that the policies can learn automatically to use turn signals to induce open a gap. So in this case, in this merge case, you have lots of basically cars, the blue cars, and there really isn't a gap to safely merge on, right? But it has learned that if you use turn signal, a gap would open up, and it's a good idea to do that. So again, this is the power of deep RL, meaning that we didn't have to hand code any of this, these kind of maneuvers or policies such as turning on turn signal into the system. It basically automatically discovered that this is a useful thing to do, and that's the advantage of power of deep RL. Okay, so our training setup is this, and what you see here is that the initial policy is trained in the midst of the so-called rule-based adaptive cruise control agents that are in blue, right? So they're very simple program agents that basically stays in your lane, does simple lane changes, not to collide with the person in front, and so on. So so after initial training, you'll have, so here's something, an edge case that's considered to be failure. What happened is that the blue car sort of tries to merge on the same middle lane, and then basically this causes the RL policy to basically go off the side. And this is essentially a problem that that simulation would basically a typical problem with simulation, which is the reinforcement learning policy trained can often overfit, and when you have a policy, when you have behavior from other agents that they're slightly different or different than the agents that are part of your training environment, then that's when potential problem can happen. So what we want to do is we want to actually turn to self-play to help with this, to improve our performance. And the way we do that is self-play, and I'll talk about this in the next slide, but it really allows us to learn really interesting behaviors from a relatively simple environment. The environment is simply just essentially a lane graph. So how do we do this? Well, so it's very simple at the high level. Instead of using these programmed AI agents or smart agents, we simply replace more agents in the environment with our neural network policy. And what you see here is that during a typical training run, typical episode, we'll sample from our existing neural network policy learned, and we'll randomly place them as sort of other sparring partners, so to speak, within our environment. And these screenshots are exactly the sort of the input rendered representation that our neural network really sees. Okay, so if we do this, let's look at how training progresses. So what you see here is the sort of the training curve for the first stage, where there's no self-play. The green is the success rate. So how often do you go from A, B, or C to D, E, or F successfully? And then you have collisions in simulation, and you have out of bounds, which means that the car went off the road. So this is really good. This is what we expect. As the number of parameters gets updated, we'll have better and better performance. That's stage one. For stage 2 and 3, what happens is that we injected other reinforcement learning agents as part of the environment. So because the distribution of the policy changed, you'll see a huge drop in performance initially, but it quickly, as we train for 1,000 iterations, it'll go back up. And for stage 3, we'll mix in with also different set of policy distributions for the other agents in the simulation, the training environment. And same kind of things happen. You'll have different stages and performance would also jump. Okay, so that's real quite simple. I mean, this self-play thing is being used in AlphaStar, amongst other sort of works from OpenAI, for example. And it's really shown to be a really good technique for adding diversity, right, to the environment. And when you have more diversity in your training environment, especially for reinforcement learning, you're gonna have more robust policy, and it'll generalize better. So let's look at some qualitative examples of some of the behaviors that are possible, that are being learned. So here you're looking at the green vehicle. We're trying to do the right lane change, and initially it braked because the car in front of it broke and then it did a lane change and merged onto yellow. Yellow is the destination lane ID. And here's another example. Now we're trying to merge onto the middle lane, and it waits for a bit and then decides, okay, I'm going to overtake because these guys are really slow in the middle. The blue cars in this example are the rule-based agents, and then the red are other reinforcement learning neural network-based policies. Here's another example. This is a similar kind of example, but in this case, if you look really closely, I don't know how, maybe you guys can't really see this, but after getting really close to the center lane, it sort of pivots back to the right lane and to automatically give itself a gap, a margin. And then finally, this is another example. This is a yielding. So this is you'll see an emergency kind of brake to yield to the car, cutting the green car off. So again, if you look at these kind of behaviors, it really is hard to hand code maneuvers like this using traditional logic, because people typically have something like going straight, you just keep in the middle of your lane, and then it's a finite state machine where now if you're doing lane change, now you'll compute a lane change curve. So compared to those kind of robotics approaches, the reinforcement learning policies are just more smooth. It's really hard to sort of qualify what they're actually doing, except that it's trying to maximize the reward that we give it. And the reward in this case would be you get a positive reward for completing the maneuver, going to the correct destination. You get a negative reward for collisions and also going out of bounds. And then you'll have some velocity sort of rewards for going at a reasonable speed and so on. So is this perfect? Well, it's not perfect. So if you look at the left example, the emergency brake example, this is kind of interesting. So what happened is that the green vehicle went through this kind of emergency deceleration, but it also noticed that it turned its wheel around. So maybe it found that this is a good way to increase the braking distance or make it easier to brake. I'm not sure, but this is the interesting kind of thing that the policy had to learn. We also have some rear end collisions that happens rarely, but it does happen. And so in these cases, the car tries to brake, but it's not able to brake hard enough or avoid a collision. So I think these are the key challenges in the future: is how do you make it more robust? How do you make collisions basically eliminate all collisions? And we can look quantitatively. So the result of the self-play is that we are able to improve performance from essentially 63% with a simple program policy all the way up to 98.2%. And then these different populations are sort of mixture of different agent types that we use for different stages, right? So if you look at the stages, stage 0, 1, 2, 3. So for stage 2, we're essentially using training with population 3. And then population 3 is a mixture between these programmed IDM agents, intelligent driving model agents, a mixture of RL agents, mixture of the first stage self-play agent. So there's different ways you can play with the mixture to synthesize the population of training agent that you want to learn from. Okay, so for more details, you guys can feel free to check out the paper on arXiv. But in summary, we've shown that self-play is really useful, but there is still sort of ways to go in terms of making it more robust and safe. So continue on. I want to talk more about a different sort of different work, but continuation on how to make it robust. In this example here, this really sort of characterize what we mean by robust. So the fact that we don't really know what the other vehicle, in this case, the gray vehicle in front of us, is really thinking about, is really leads to inherent uncertainty or stochasticity in the future reward, the future value of the state, right? So the person in front of us could be aggressive, they could yield to us, or they could not let us make the turn. So we don't really know. And the question is, in the face of this uncertainty, how are we able to make robust decisions and safe decisions? And so for this, we introduced something called what we call worst cases policy gradients. And the idea here is that because there's inherent uncertainty in the environment, what we want to do is we want to model the entire return, not as a single scalar, but as a distribution. Okay, so we're still going to use something like actor critic. This is a standard reinforcement learning technique in the space. But the critic, instead of outputting a single Q value, which is a scalar, is going to learn to model the entire distribution. And then we're going to optimize for risk-sensitive criteria. In this case, we'll talk about the criteria in the next slide. But this really is a modification so that we can actually have better generalization, better robustness. So how do we actually do this? Okay, so in this case, the environment here would be, the entire environment would be the state. And then our green sort of trajectory could be action. The action could be just simply step on the gas and turn the wheel, or it could be a trajectory, right? So that could be, so any of those things could be an action. And now if you look at what standard RL is doing, or even distributional RL, is that it's trying to maximize the red bar. So the red bar indicates the Q function. The Q is the expected future return. And so it's trying to adjust the policy so that we can push the red bar to the right. Now, in contrast with worst cases policy gradient, what we're proposing is that we're proposing to optimize not for the entire expectation of the entire distribution, but rather the expectation only up to the alpha percentile of the distribution, right? So we're saying that we don't care about the average expected return. We care about what the best return would be under the worst possible scenarios, right? So the future return is a scalar value. The worst case scenario is where the future return is negative. In this case, a collision or near miss. So that's essentially the main difference. Now, if we do that, what that really means is that we would prefer the policy theta 1 over policy theta 2. Okay, even though if theta 1 has a lower expectation, that's the yellow. And the reason is because it has a lower variance, right? So it has a higher conditional value at risk. That's what CVAR means. So that's what we're essentially optimizing for. Now, how do we actually do this? So again, the first thing is that the return is not a scalar anymore. The return is actually a distribution, so it's a random variable that's called Z. And what we're going to do is we're going to make our critic to model both the mean and the variance over the Z. So we're assuming this is a Gaussian distribution, and the reason is that this will lead to a really nice closed form computation for the CVAR. And because we have a distribution, then we have an equivalent distributional Bellman operator, right? So instead of the normal Bellman operator, Bellman equation, we'll have a distributional version of it. And I won't go into too much details of the math, but the update is basically, there's two parts to it. The first part is the standard, the update with the Q, so the Bellman operator that you would use for Q learning. The second part is this epsilon, which represents our variance of the Z, of the future return. And the derivation basically shows that we can also relate the variance from state S prime and A prime, which is the future state, to our current state S and A. So this is sort of the equivalent backup for the variance in sort of the TD learning sense. And then once we have that, we're going to update so this will be the target epsilon, target distribution over the future. We're going to optimize the Wasserstein metric from our predicted distribution with the target distribution. So this is just so now we have a way to update our critic. So with that, how do we update our actor? So what we do is we take our critic and given our estimate of the distribution over Z, the future return, we can compute our this gamma pi value, and this is the conditional value at risk. And we can compute it in closed form because this relates to the CDF and PDF, the standard normal distribution. So it's really quick to compute. And this is highlighted in red. And so what we're going to do is we're going to take the conditional value at risk up gamma pi, and we're going to back propagate it through our critic, and then also through our actor. Our overall objective, this is the standard policy gradient objective, is denoted as integral over the states and then integral over the different actions weighted by this CVAR, conditional value risk epsilon pi term that substitutes essentially our Q function. And we have a theorem in the paper that shows that using sort of the similar approach as the policy gradient theorem, we can turn this into the gradient into a gradient expectation and the gradient of the log of the policy, again, weighted by this gamma value. So the one interesting thing here that we have that falls essentially out of the fact that our gamma pi is conditioned by the alpha is we have this alpha knob, right? So you can think of this as a scalar that goes from 0 to 1. And if it approaches 0, the policy itself will become very risk averse. If alpha goes to 1, this becomes risk neutral, and this essentially would basically fall into a standard sort of active critic DDPG kind of style. And this really gives us a sort of a family of policies that are that will be risk aware, and then so that's kind of interesting. So in the end, in summary, worst case policy gradient we're proposing is a combination of distribution of RL, conditional value at risk, and then the standard deep deterministic policy gradients. It's computationally efficient because we don't have to, unlike other sort of papers, there's a few other papers related to optimizing for CVAR. Some of them require sampling. In this case, we have a closed form computation. And at the very high level, since instead of having a 1D output for our critic, we have a 2-dimensional output. And then there's extensions where you can have a mixture of Gaussians or a mixture of other kind of distributions as well. But right now, with the simplest case, essentially just one more dimension for your critic. And again, this leads to a family of risk-sensitive policies. Okay, so what happens here is that similar environment we perform experiments on that showed earlier, and I want to show you some experimental results. So what you're looking at, this plot is basically a plot of the average episodic test reward as a function of the alpha knob that I showed earlier, right? So as we turn alpha this way, becomes lower, the variance decreases as expected, and we don't have any collision. So collision would, in this case, give a negative 50 reward. As you see, it basically limits collisions, which makes sense. What also that leads to is that the average time it takes to finish this episode of making an unprotected left turn would be increased because qualitatively it just waits for a bigger gap before it makes the maneuver, which makes sense as well. And then lastly, the estimated uncertainty also decreases as a smaller alpha. So that's how expected. For the merge scenario, it's similar kind of trends, which makes a lot of sense as well. Okay, so one of the interesting things is that because our critic can now estimate uncertainty over the future discounted returns, we can actually look at in real life what is the known estimate to say, right? So in this example, as the green car approaches the intersection, you see that the sigma, which is the estimated uncertainty, rises, and it reaches a peak when we're crossing onto oncoming vehicle. And then quickly it'll decrease as we sort of finishes the maneuver, which also makes sense. Here are more examples of under other situations how this does. So again, this all makes sense. This is exactly what we intended the framework to learn, and does that. We also have tried similar experiments in Carla, similar kinds of left turn scenario and a merge scenario, and in all these cases, you notice that when alpha is smaller, it takes longer to finish a maneuver. It's more cautious, more conservative. In fact, in this case, there's actually a collision simulation that actually happened with alpha. It's had to be 1. Quantitatively, what you're looking at here is generalization performance. Okay, so we're taking the top table is the left turn, and the bottom one is the merge. And what we're doing here is for the testing environments, we're going to actually add more velocity to these different, the speed of the other agents. We're going to spawn them more. That creates more vehicles on the road. So basically test out generalization. So these hyperparameters of the environments have not been used in training. And what we see is that with standard approaches like DDPG and proximal policy gradients, optimization, and even the distributional RL ones like C51 and D4PG, it's really, really hard to get the collision rates to 0. It's just because they're not optimizing for risk-aware, risk-sensitive criterion. But with worst case policy gradients, we are able to push it close to 0, even though there's still some collisions when we set alpha to be small. So this is I think this is really where, in order for this to be on the road, for this to go in real life, we really need to make sure that the collision is definitely 0. So again, this is in summary. This is I think this is interesting work, but it's far from finished. We really need to ensure robustness, not just only in simulation, but in all sorts of different environments, and potentially one day to real world. We need to increase the realism of the simulation, and then we need to also make sure that the policy is comfortable, and also the trajectory is smooth. So for more information, this paper is also on arXiv. It was published in Corel last year. So with that, thank you very much. I think people are converging on these kind of very interesting techniques with RL. So yeah, so thank you, and thanks to my collaborators. And I'm happy to take some questions.
Okay, great. I think we got several questions.
Okay.
So one is, so the first question is, are there any traffic, so other traffic participate program to make room when there is a right turning signal?
That's a really good question, Zoltan. So let's see here. Let me see if I can share my screen again. So in order to have stochasticity, this is a really good question, in the environment, in this case, what happens is that the oncoming vehicle would have a randomly samples from one of 3 types of modes. So one is, be aggressive and don't yield. The second mode is actually yielding, so we'll brake if it sees the green vehicle is trying to make a left turn. And the third mode is simply ignore it, ignore the vehicle. So, and because of these 3 modes that it samples randomly, this really leads to a more, in my opinion, a more realistic simulation of what the actual environment, like in the real world, happens, are like. And that leads to uncertainty. So to answer your question, it's randomly, stochastically picking one of these 3 modes.
Okay. So the second question is that during the self-play, is it possible for successive generations to keep switching between passive and aggressive behaviors, as they realize they can either take advantage of or take refuge from previous generations?
Okay, so yes, so what happens is that in self-play, there's many ways to do this, and typically you would keep a population of different agents. So, and by population I mean the checkpoint weights, RL weights. So, so what you can do is, so I don't actually do this now, but as an extension, what you can do is you can actually cluster these policies according to the kind of behaviors, and then you can make sure that you try to get as diverse sort of set of agent policies as possible during training. So in this case, it doesn't, in this case, this is it sort of converge, and so I don't have a definitive sort of thought on how does it either converge, or does the policy keep sort of, I guess this is the question you're asking, right? Does it goes from oscillate, does not converge. So I think that's really good future work to examine what happened. Does it converge to a Nash, for example? But this is a general sum game, so so I think it's I think we can take inspiration also from the AlphaStar kind of work, where it's just you just have a set of diverse policies that are there, and then so they don't necessarily converge because these different policies are trained with different training distribution.
Okay, and then we got a third question is that does the policy from the self-play provide any information into which aspect of the prediction are important?
Yeah, that's a good question. So I think it's just you might be able to deconstruct or introspect as to what aspect of prediction is important, but it's really hard to do. And so the reason is because the policy that's being learned is simply gives action, the next time step action, and it's training the model free kind of sense. So, and I think this is another question here I see in the chat, model-based RL. So that's actually also a good question. So if you do model-based RL kind of simulation, then potentially the longer horizon plan that you come up with might have better correlation, or maybe tell you which aspect of prediction is important. But right now, it's hard to really see which aspect of prediction, just because they operate very differently. With predictions, again, it has to be interactive predictions, right? You have to predict how others will react to your actions. So I think it's interesting, but it's not really apparent to me what aspect of predictions is important. Now, we do have you know we do have attention-based encodings, and what that does is that tells you which agents are relevant, because if you use attention, you can actually tell that as part of the encoding process, which other agents or cars on the road is not really relevant for my predictions or my actions. So, and that's what you expect in terms of the distance to the ego or self-driving car really is inversely proportional to how important they are.
Okay, I think following that question, also there's one more, like, do you have any insights into how the learned agents are predicting the world, or like this is really like a purely reactive?
So yes, so right now with the self-play, it's purely reactive. So, but the thing is, I'm always surprised by how interesting behaviors can learn just from a reactive policy. And it really has to do with distillation of the examples into a reactive policy. So I think moving forward, I think one of the few examples that you see from the collisions could be helped by using a model-based sort of policy. So with the model-based policy, if you think about it, it's basically saying that if my assumption is right, if I'm assuming that the vehicle in front of me would have constant deceleration or constant velocity, then with model-based like MPC or ILQR, you're guaranteed not to collide, right? If it's within the reason of my deceleration of my car. So that's what you get. So that's the advantage of guaranteeing non-collision in these kind of scenarios. The disadvantage is that if you're in a dense merge scenario, right? If you want to squeeze into a closed gap, right? If you want to induce open a gap, then model-based is not going to help you that much, because you have to be able to, because your assumption of constant velocity, constant acceleration, and constant steering just goes out the window. And I think that's where model free comes in. So I think as a human driver, I suspect we have a mix of both things. If we're just cruising on a highway or freeway, we're probably in the model free kind of mode. But now if we're trying to make a sharp turn onto a busy major road, and at least for me, I see myself trying to anticipate or visualize how in the future, and that would be considered to be model-based planning. So I think the question is, how do you combine the two to achieve more robustness? I think to me, that's a good future direction.
Great. Thank you, Charlie. So I think due to the time limit, we have to go do you mind like replying in the chat?
Sure, absolutely. Absolutely. Thank you guys again. Thanks so much.
And then you can unstop share your screen.